Today, let us discuss about the solubility of a gas in a liquid. Okay, this is the very important chemistry. Okay, so here, solubility. So first, let me tell you the solubility. What do you mean by solubility? So solubility means what? Degree of dissolution. Okay, right here. Degree of dissolution. Okay, dissolution of one component. Let me write one substance. Okay, in a one of the component that may be the solvent. That is another component. Another component, that is the another substance. So here, what is the degree of dissolution of one substance in another substance? So some of these substances having a very high degree of dissolution, and some of the substances are very less degree of dissolution. Okay, that is depends on the nature of the substance and the nature of the another substance, right? Okay, so mostly the substance which are we using here, our waters, we can say the some are the polar solvent, some are non-polar solvent. Okay, so as we know in our lower classes, like dissolved, like that means polar substances are soluble in the polar solvent, and the non-polar substances are soluble in non-polar solvent. That's we learn at lower classes. Here solubility means the degree of dissolution of one substance in another substance. Right? Okay. As we know in solutions, we have two different component. One is the smaller proportion that we consider as the solute, another is the larger proportion what we consider as the solvent here. Okay, now here, so solubility of a gas in a liquid. Okay, so we have a different factors affecting on the solubility of a gas in a liquid. Okay, one of the most important factors. What are the important factors? So number one, nature of our gas, nature of gas. Okay, or the nature of the liquid what we using here, right? Okay, let me keep aside the liquid. Okay, so the first let we discuss about the nature of the gas. Okay, so just try to remember some common gases which are available in our atmosphere. You know, hydrogen gas, right? Then nitrogen gas, oxygen gas. Then even halogen also, chlorine gas. Fluorine gas also, right? Then carbon dioxide gas, nitrogen dioxide, sulfur dioxide, even HCl. These are also the gas. So these gases are available in our atmosphere, right? So the most abundant one is we can consider the oxygen, we can consider the carbon dioxide, we can consider sulfur dioxide, which are produced from the industrial in industries. So now see, these are the different gas. Different gas have a different solubility in a particular solvent, right? So one of the very important chemistry we should know that in the given liquid, so the gas given here, what is the chemistry behind it? Number one, right? So this gas, so if there is the interaction between the gas and the liquid, that gas can dissolve in that solvent very easily, and those gas which does not interact with the given liquid, that gas, it's difficult to dissolve in that liquid. That's the very common sense we must understand. So beside that concept, let me just give you the simple concept here. See, some of the gas are heavier, some of the gas are very light, okay? As you know that due to our uh, gravitational force, some of the gas is very closer to our Earth's surface, some of the gas are just goes very high altitude, as we know, right? See, hydrogen gas is not available here in our Earth's surface. This hydrogen gas is very available in the very high altitude. Not only hydrogen gas, the other gas or noble gases, as we know, noble gases, helium gas, even this gas also available in our very high altitude of the atmosphere, and some of the gas is very close to our Earth's surface. Why these gas are very close to our Earth's surface? Some of the gas, why they are available in the very high altitude? One of the very simple basic thing is their masses. See, some of the gas are very light, those gas which are very light, are available in high altitude, and those gas which are heavier in their mass, they are very close to our Earth's surface. Those gas which are heavier, it can be dissolved, into our given solvent like the water also. See, carbon dioxide is very close to the surface of the water, because it's very heavier, and the oxygen also very somehow closer to our surface of the water. So carbon dioxide is very easy to enter into the waters. Then oxygen also can enter to the water. Therefore, this oxygen is also dissolved in the water. That oxygen, what we call dissolved oxygen, and the carbon dioxide which enter into the water. That carbon dioxide we call the dissolved carbon dioxide. So these oxygens are dissolved into the water. That oxygen can consumed by the aquatic species like the fishes, right? Now these are the different gases which can be dissolved in our liquids. Number 2 factor is temperature. What is the effect of temperature? What is the effect of temperature? Effect of temperature, right? So now here in our atmospheric temperature, some are very hot, some are in some regions are very hot, in some regions are very hot, and some regions are very cold. As we know, gas is always free to move at very high temperature, because all the gas molecules are far away to each other, right? So they can move very freely. So here we can know the effect, what the effect of temperature. In the cold regions, the gas molecules comes closer. Understand? In the very hotter region, the gas molecules are very far away and can move very freely. Understand? Then these gases at high temperature means the very hotter region. So the gas is very free to move, and it's difficult to dissolve into the given liquids, remember. But in the colder region, the gas comes closer, right? So once the gas comes closer, it's now becoming very heavier, as you know. So that gas is closer to the surface of the liquid. So that gas can easily dissolve into the given liquid. So that means, so the solubility of the gas in a liquid increase with decrease the temperature, right? So let me say again, the solubility of a gas in a liquid, increases, with decrease the temperature. When the temperature falling down, the gas can be soluble easier than the hotter region. So as we know, the our aquatic species like the fishes, that we can consider that aquatic species are very comfortable in the colder water, cold water rather than warm water, because okay, the oxygen gas, this oxygen gas, right, okay, are okay more dissolved in the cold water rather than the warm water. See, even in the warm water, when we drink, that oxygen, okay, quantity is very less compared to the cold water. That means the oxygen can dissolve in our water, okay, more easily in the cold water, I mean in the colder region than the hotter region. Therefore, the aquatic animals like the fishes are very comfortable in the cold waters than rather than the okay warm waters. Don't forget. Understand? So that's the effect of the temperature. So I repeat it once again. So what is the effect of the temperature on the solubility of a gas in a liquid? So I now repeat it here. The solubility of a gas in a liquid, okay, increases with decrease the temperature. One of the application, as I mentioned before, that is aquatic animals, aquatic species are very comfortable in the cold waters rather than in the warm waters. Okay, remember, okay? Then now here, the most important factors, that is the effect of pressure. So what is the pressure? That is the force per given area, right? Say we have a two different pressure. One is the external pressure, another is the internal pressure. So any substance, even our cell also, we have our internal pressure, and the other substance, even the liquid also having their own pressure. Okay, so that liquid trying to escape as a vapor, that pressure, what we call a vapor pressure, that one cases. In the case of the gas, you know, the gas molecules is around here in our atmosphere. This gas is always trying to fly away, it's always trying to move freely, right? So how can this gas, okay, can enter into the, okay, into the our, okay, liquid? That may mention I write here water, right? So how these gases can enter into the water molecules? So number one, see, gas always goes to freely, right? So how we can keep, how we can this gas let into the, okay, liquid molecules? See, number one is the external pressure. See, this pressure, when we press more, this gas can come closer to the liquid surface. If the gas, I mean if the pressure applied more, so this gas can enter into the liquid molecules. That means what is the solubility of gas in a liquid? That is, okay, the solubility of a gas in a liquid increases with increase the pressure, right? So here as a particular the gas, as a whole the pressure we consider. So some partial pressure we applied on the gases which can enter into the liquid. That pressure we can consider as partial pressure. Okay, some fraction of the pressure we can apply here, okay, on the gases molecules, okay, the gas molecules. That gas can easily enter into the water, I mean liquid molecules. So therefore the gas can be soluble in the, okay, liquid by applying the more pressure. That means solubility of a gas in a liquid is increasing, okay, with increase the pressure. That means solubility of gas in a liquid is directly proportional to the our external atmospheric pressure. That we remember. Okay. Now here, how much gas can be soluble? How much gas can dissolve in our particular liquid? That is depends on the how much pressure we applied on the gas, right? So that means solubility of the gas. Solubility, as we know, okay, as we define as the solubility is the degree of dissolution. Degree of dissolution means how much the substance can dissolve. That amount, that quantity we can consider as the solubility of the particular substance. So solubility of a gas, that I consider a gas, okay, but a solubility as we consider as the quantity of the substance. So how much quantity of a substance can be dissolved into a liquid, that we can consider solubility, right? So solubility of the gas we can express. We can express as amount of gas, right? Dissolved. That means, right? How much amount of the gas can be dissolved? This amount we can express the mass of a gas dissolved. This mass, let me write M. How much the mass of the gas dissolved in a particular volume of in a liquid, right? That's we can consider how much the degree of dissolution of the gas in a liquid. That's the solubility of the gas. So this solubility of the gas we can express as in terms of the mass of the gas, right? Then another one, we can also express in terms of the number of the moles, right? So this number of the moles, the standard terminology we can use, that is the mole fraction. Okay, mole fraction of the gas. How much mole of the gas can be dissolved into the particular volume of the liquid? That's the amount of that's the mole fraction of the gas we also consider as solubility of the gas. So here the mole fraction of the gas, the mole fraction, the letter which I using here is small x. X is the mole fraction, right? So these two terms we use in the place of the solubility of a gas, right? So as I said before, the solubility of the gas in a liquid is directly proportional to our pressure. That pressure we can consider as the partial pressure or atmospheric pressure. Clear? Now here, this mass of the gas dissolved or the mole fraction of the gas dissolved is directly proportional to the partial pressure. That's what I can write. This is the mass of the gas dissolved. Is directly proportional to the partial pressure. Let me write a partial pressure. Partial pressure means the atmospheric pressure. Some fraction of the pressure we applied on the gas. That is the partial pressure. Let me write here P. That I write M directly proportional to the P. This. So when the pressure is more, the mass of the gas dissolves more. That means directly related to each other. Now here, the mole fraction of the gas dissolved is also directly proportional to the P. So this is the our mathematical relation between the mass of the mass of the gas dissolved or mole fraction of the gas dissolved directly proportional to the partial pressure. So this relation, one of the scientists established. So the name of the scientist is John Henry, right? So according to him, so this is the what we call Henry's law. So what is the Henry's law? This is the law, based on, this is the law of the solubility of a gas in a liquid. Number one, this is the law. What the law? Solubility of a gas in a liquid. Now here, when we are talking about solubility of gas in a liquid, so we consider we are discussing three different factors. One of the factor is nature of the gas. Number two factor is the effect of temperature. The number three factor, the third one, is the effect of pressure. So the most important factor in this law, that is the effect of the pressure. So this law obeying the effect of pressure on solubility of gas in a liquid. Don't forget, right? What is the name of the law? What is the name of the law? Obeys the effect of the pressure on solubility of a gas in a liquid. That is the Henry's law. Don't forget, right? What is the Henry's law? Simple logic is relation between the mass of the gas dissolved, and the partial pressure or atmospheric pressure or the mole fraction of the gas dissolved and the partial pressure or atmospheric. Okay, so this is the relation between these two. So this is the law what we should remember here. Now here, according to the Henry's law, about solubility of the gas, see, mathematically we can write this proportionality sign. When we remove, we just replace by the constant. One of the constant I write here KH, that is the P, and when we use this equation X, that is the mole fraction, so now here I write KHP. So now here, what is the KH? That is what is the important. Here in this equation, this KH is the proportionality constant, right? So this equation, what we derived, that what we established, that is from the Henry's law. Now according to this law, so this KH, what we call, that is the Henry's law constant, right? This is the Henry's law constant, right? Now here, this Henry's law constant, right? So this Henry's law constant, what's the role of this? See, look at here. So the values of the KH, that means Henry's law constant, okay, are different in different gases. Don't forget, number one. Okay, now here I just write here, this KH value is always depends on the partial pressure, that means pressure, right? See, you know the what is the pressure, right? And what are the units of the pressure? See, sometimes we use the unit of pressure in atmosphere, and sometimes the unit of pressure we use in the bar. Sometimes, okay, that we can use, we write a Newton per meter. Sometimes we can use the millimeter of the mercury levels in our barometers, right? So now here, the KH value depends on the partial pressure. Sometimes this KH value, right? Okay, what's the values given? So as I mentioned before, the KH values are different in different gases, right? Some of the gas, the KH value is very small, and some of the gas, the KH value is very high. Clear? And now here, number one, I just tell you the KH values are different in different gases. And number two, right? Different in different gases. Number two, this KH value also depends on the temperature, right? So this KH value, right, different at a different temperature. Don't forget, this KH value is given in your K textbooks. So you can compare what are the KH values of the different gases. So you can see that what is the KH value of the oxygen, what's the KH value of the hydrogen, what's the KH value of the helium, what's the KH value of the carbon dioxide, what's the KH value of the different gases. We just listed in the K books in your K textbook. Now when we compare the KH value, okay, those gas having the high KH value, right? Those gas having the high KH value are less soluble in a particular liquid. Suppose we have the liquid water, right? See, for example, helium, the KH value is very high compared to the other gases, carbon dioxide, oxygen, HCl, nitrogen, right? Therefore, this helium is very less soluble in our water. What's the KH value is very higher than the other, what we mentioned, the common gases, carbon dioxide, sulfur dioxide, etc. Right? That means the solubility of the gas, okay, increases with decrease the KH value at particular temperature. Don't forget, right? Let me repeat it once again, right? The solubility of the gas increase with decrease the KH value, right? for example, right, say helium, the KS value is very higher than the oxygen, carbon dioxide, okay, than sulfur dioxide. As we know, the sulfur dioxide gas value is very less compared to the oxygen, compared to the carbon dioxide. Sulfur dioxide can dissolve into the water very easily as compared to the carbon dioxide, as compared to the oxygen, right? So don't forget. And at the temperature different, this gas value also different, right? Okay. Now here. So when we do the calculations, okay, how much the mass of the gas can be dissolved in our given volume of our liquid, right? And what the mole fraction of our gas, okay, which can be dissolved in our given volume of our liquid, that are almost directly proportional to the partial pressure, right? So when we do the calculation, the solubility of the gas, we can calculate in terms of the mole, I mean in terms of the number of the moles, in terms of the mass, okay, in terms of the gram, how much gram of the gas can be dissolved, right? Don't forget. Now here, see, when we just let we understand what is the unit of the mass. See, when we consider this mass, obviously it should be gram, right? In gram, right? Then what about the pressure? So this pressure is supposed to be what would be? That may be the atmosphere, that may be the bar, that may be Newton per meter, that may be the some meter per, okay, that area. Then that may be the millimeter of the mercury. So most common units that can be as atmosphere and the bar. These are the very common units of our pressure, right? Now here, when we do the calculation, so when we do calculate the KS value, so mathematically we know that M divided by P, that is we write grams per atmosphere. We can write like this by using atmosphere, right? So when we use the mass in a gram, so we can do like that. But the most general equation we use, that is the mole fraction, right? See, no, mole fraction. What is the mole fraction? See, this is the ratio of the number of the moles of the one component and the total number of the moles of all the components present in our solution. Solution means gas and the liquid. Now here, so when we do write it now, this is the number of the moles. Then here also number of the moles when we do calculate. So number of the moles when we cancel. So the mole fraction. So when we calculate, no units. Don't forget, no unit. And when we have the pressure. Pressure obviously we have the units. So it can be atmosphere, it can be bar, it can be this and that. Okay. So when we have this is the atmosphere, right? So sometimes see when we apply this back equation. So when we calculate the KS value, when we apply this x divided by p. So if we don't have the no unit because the mole fraction, no unit. Suppose this pressure, if we give it here atmosphere, what will be the unit of the case? Here should be the atmosphere inverse, that means per atmosphere, right? So now my point is, this KS value, as I said, it depends on the pressure, right? Sometimes this KS value, see, look at x is directly proportional to the p, right? This p can also write here, this x can also write here. When we change the position of the x and the p, the unit of the KS also be changing, right? So now remember, the unit of the KS, it depends on the pressure, right? Sometimes this KS value is given here per atmosphere, right? If the KS value is given in per atmosphere, what equation should be used here? That should be that x is equal to KS P. Don't forget, right? So if the KS value is given in per atmosphere, don't forget, we have to use this one, right? And so By giving the pressure, we can calculate the mole fraction. By giving the mole fraction, we can calculate the P, since the KH value is given in the per atmosphere. Instead, if the KH value is given here atmosphere or bar something else, the unit of the pressure, as I said before, the value of the KH is always depends on the partial pressure or pressure. Clear? So now here, sometimes this KH value also given in the atmosphere, right? If the KH value is given in the atmosphere, suppose we are going to calculate one of them, that is the mole fraction, right? So this P value is given. Suppose this P value is, let me write, 1 atmosphere is given, right? So when we are going to calculate, if we apply this, see, look at, when we put it like this, suppose I put this 2 atmosphere, suppose I give it a KH value is 2 atmosphere, P is given 1 atmosphere. When we do calculate by using this equation, what will be the unit of the X? Let us see. KH, that is the 2 atmosphere, and what is the P is given here, 1 atmosphere. So when we do calculate 2 atmosphere square, so this 2 atmosphere square is not a unit of the mole fraction, so we cannot apply this equation. Don't forget, according to the value of the KH, according to the unit of the KH values given, so we have to change. So what should we change? Instead to use this one, we have to use like this, right? See, now when we are going to calculate the X value, how do we calculate X value? By using this equation. Now P divided by KH. So here P given here atmosphere, here also given here atmosphere can cancel, and we found no units. So we have to use this equation if the KH value is given in the atmosphere. Don't forget. So this is the very important logic we should remember. Okay. Now we have the different this law here when we are discussing about solubility of a gas in a liquid. See, this law, what we discussing Henry's law, okay, what type of the solution of the gas in a liquid, what type of solution. See, when we take the gas, when we take the liquid, so that gas and liquid should not be interaction, no reaction. Okay, if the reaction takes place between the gas and the liquid, so this Henry's law does not validate, no validated, right? That means Henry's law validated only the gas should not interaction with the liquids given, no reaction at all, right? That's type of the solution. So gas, what we know it. See, in our gas here, gas. See, under any conditions like the temperature, whenever you change the temperature, whenever you change the pressure, under any condition of temperature and pressure, very few, even a negligible gas remain gas. When we change the temperature, when we change the pressure, gas automatically starting to change into the liquid form. Because the gas, when the temperatures come close, very cold, in the colder regions, gas molecule come closer. Once the distance between the gas molecule come closer, if that distance reach to the distance between the liquid molecules, so that gas molecules that gas is started converted into the liquid form. Because the liquid and the gas, what's the simple difference is the distance between the molecules in the gases is very far away to each other as compared to the distance between the molecules present in the liquid. That means liquid molecules. So that idea of what we can approach, what we can relate to the density. So as we know, density of the liquid is much more density than the density of the gas, right? Now here, So when we change the temperature, gas tends to change into the liquid. When we change the pressure, also the gas tends into the liquid in liquid nature. So now here, those gas which remain gas under any condition of the temperature and the pressure, that gas, what shall we call? Do you remember? What should we call? That is ideal gas. So ideality is very rare. It's very rare. Even you also, as can we consider you are the ideal student? No. Can myself consider as the ideal teacher? No. Right? So ideal one is the very rare. Very rare. But it must be there. It must be there as we know. Right? So the gas which we consider as the ideal gas means gas remain gas under any condition, wherever I mean the colder region we go, that gas remain gas. When we go to the water, the gas remain gas. When we go to the high pressure, when we apply the very high pressure, gas remain gas, right? So that types of the gas we call the ideal gas. So when such types of the gas we dissolve into the given particular liquid, right? So gas should be remain as the gas into the liquid. That means this Henry's law only obeys the gas should not be interact with the liquid, right? Number one. And number two, those gas, okay, so it should not be interact. Okay, that means no reaction. No reaction. Say for example, HCl. When we take the HCl, right, plus, so when we dissolve into the water, right, so this HCl it dissociate into the ion. That means it should be associated with the water. It should be associated with the water. That means in our water, this HCl not remain as HCl. So this HCl is formed ion, and means in ionic form that the HCl is present in our water. So therefore this HCl when dissolved into the water, so we cannot explain by Henry's law. Even the ammonia also, when we dissolve into water, so this ammonia, it can form the ammonium hydroxide. So that can be form the compound. That means some of the gas can undergo dissociation, some of the gas can undergo the association in the given liquid substances, right? Those gas which undergo dissociation, which undergo association, that gas we cannot just consider in our Henry's law. So therefore I just mentioned here, why don't we consider Henry's law when we dissolve HCl gas into the water? Because dissociation takes place. Then why don't we consider ammonia gas into the water in our Henry's law? Because this ammonia also undergoes association, right? That's we can. Now here we have some application of this solubility of the gas in our liquid, right? So very simple application, as we know, the like soft drink, cold drink, even our beverage drink. So these drinks, see, while they're packing the bottle which are available in our market, the care which are provided is very tightly covered, right? And so when just having the party, as you know, when we have the party, when we celebrate the birthday, when we celebrate some some functions. So even in the sports, those who are winning the sports events, they celebrate by just opening the cake and just set the bottle and flush out the liquid one which are present inside the bottle, just is flush out. So why that things can show it? That means inside a bottle they fill up the carbon dioxide gases like the carbonate drinks. Okay, see Coca-Cola, Pepsi, soft drinks. Okay, when we set the bottle and once we open the cap, so that liquid is flushed out very high. That means the carbon dioxide gas is filled into the bottle, applying the external pressure, right? So due to the very high pressure, that gas is passing into the liquid. When we release the pressure, the gas comes out. When we press, when we apply the pressure, gas entering into the liquid. This is the one of the application of our Henry's law, right? So this is the very important idea about the solubility of our gas in a liquid, right? Then secondly, solubility of a. Now here I mentioned liquid. In a liquid, here I just take it two components. One is the one liquid, another also another liquid, right? That means liquid mixture. Okay, and here the another component we can take the solid also, right? So here, so the physical properties of the liquid, what should we remember it here? Some of the liquid, we have two different liquids. We have two different liquids in our around of you. So one of the liquids, so when we open, when the liquids are available in our open container, some of the liquids remain as liquid as long as possible, and some of the liquids, when we store it in open container, open vessel, so that liquids may not be longer remain as liquid, it's dry out, right? So why these different liquids, and why these liquids remain as liquid, why the other liquids does not remain as liquid? One of the very important, that is, so we have two different. One is the liquid which can easily vaporize. That liquid we can say the volatile liquid, or solid also volatile solid. See camphor, camphor. So when we have a camphor, that camphor when we place in the open container, so that camphor without converting into the liquid, that liquid solid, it can be vaporized, right? That types of this solid we can call the volatile substances. So some of the liquids are the non-volatile. That means does not volatile, does not vaporize easily. So some of the liquids, some of the substances are volatile, some of the substances are non-volatiles, right? See, in the case of the liquid, as we know, the alcohol, ethyl alcohol, as you know, ethyl alcohol, when you bring here, so it should be stored in the very closed bottle. When you open it, so while you place it, while you leave inside it, so that ethyl alcohol may not be longer as ethyl alcohol, so it will be vaporizes, right? So after a few days, so that ethyl alcohol may not be remain as the ethyl alcohol liquid. Say like the petrol, as you know, in our market, petrol always just kept in the tight bottles, like. So once the petrols, when even in our vehicles, right? So your the tanky, the lockers that's kept here, once you open it, so when you observe it, the petrol vapor is very quickly comes out. That means these types of the liquids are volatile liquid or volatile substance. Even water, if the water is like the petrol, right? So we cannot find our liquid water for drinking, right? So it will be very problem for us, right? So the water, as we can consider as the non-volatile substance or liquids, right? So now here, so liquids we can classify into two categories. One is the volatile, another is the non-volatile, right? Okay. So solubility of the liquid in a liquid. So liquid itself, as we know, we have a different physical properties of the liquid. So I think you remember what are the physical properties of the physical characteristic properties of the liquid. The most important physical characteristic, important properties is, right, that is the vapor pressure. As I said before, every substance, even our cell also, even you also, even this also. So you imagine, okay, this substance itself have own pressure, that is internal pressure, right? So if, and another one is external pressure, right? If the internal pressure is higher than the external pressure, this marker, as I show you, it will be, okay, becoming bigger in size. Even we have our internal pressure. Since if our internal pressure is the more than our external pressure, our body also will be more expanded, right? So we cannot control our size of our body. Even the water also, right? Because of our external atmospheric pressure, right? So water remains as a water. When we release this atmospheric pressure, this water will be goes up as a vapor. That means, so every substance itself, they have the internal pressure which can escape, right? So that pressure, what we can consider in our liquid, that is the vapor pressure. So vapor pressure is the properties of the liquid, don't forget. So vapor pressure is the properties of the liquid. So this vapor pressure playing a very important role, okay, in other properties of the liquid, right? So don't forget. Now here, high vapor pressure and low vapor pressure. Do you understand? Understand what's the meaning of this? See, vapor pressure means, in a very simple language, I should say that is the escaping tendency of the liquid into the vapor. Some of the liquid having the high escaping tendency, like the petrol having the high escaping tendency. So that petrol liquid one can escape very quickly. So that means petrol having the high escaping tendency. But that escaping tendency we term in our chemistry as the vapor pressure. So now petrol, as I consider as high vapor pressure compared to the water. Water. So water we can keep it here as remain as water as long as possible, because water itself very low vapor pressure, right? So which liquid high vapor pressure means which liquid easier to escape as a vapor, which liquid difficult to escape as a vapor. So easier one high vapor pressure, difficult one means low vapor pressure, right? So vapor pressure is the one of the most important properties of our liquid. In order to understand about some more physical properties of the liquid, what are the other properties of the liquid? See, I just tell you, boiling point is the one of the key properties of the liquid. Freezing point, evaporation, then vaporization, that are properties. And even the one of the our new properties of the our liquid, that is the osmosis. So this is our properties of liquid. So please remember, osmosis is the very new terms for you, is the properties of the liquid. Don't forget. Now here, as I just telling you about the vapor pressure, right? Vapor pressure. So I repeat it once again. What do you mean by vapor pressure? Let me answer. Vapor pressure is the properties of the liquid. What type of the property is the escaping tendency of a liquid, right? So as per the definition, you can see in your books, the very nice definition is written here. That definition you try to remember. The easier language, what should we can understand vapor pressure means is the properties of liquid and is the escaping tendency of liquid into the vapor phases. Right. Now here, what are the important factors affecting on the vapor pressure of a liquid? Number one, as I tell you, that is liquid. So we have a different types of the liquids. Different types of the liquid means different nature of the liquids. You know the liquid molecules, right? The liquid molecules, between the liquid molecules, so the molecules are binding together by the some weak forces. That types of the force we can consider as intermolecular attraction. The intermolecular force of attraction, some liquids are very weak, some liquids are very strong. Those liquids having the strong intermolecular force of attraction, that liquid is difficult to escape as a vapor, right? That types of the liquid we can consider low vapor pressure. Say for example, water molecule. The water molecule, the molecules are binding together by the force of attraction. So the bond between the water molecule, the bond that is what we call intermolecular hydrogen bonding, right? So the polar molecule, so it can be binding together by, through the hydrogen bond. Some of the molecules, it's say inside the liquid, so some of the hydrogen bonds form the molecule itself. That hydrogen bond, what we call intra-hydrogen molecule, hydrogen bond. Another one is between the molecules, the hydrogen bond between the two molecules, that is what we call intermolecular hydrogen bonding. Another is intramolecular hydrogen bond. So those liquids having only the intramolecular hydrogen bonding. Those liquid or those substances having only the intramolecular hydrogen bond means hydrogen bond from molecule itself. That's what we call intramolecule. That molecule is always free from the other molecules. So that molecule can easily get vaporized. Another type of the hydrogen bond is intermolecular. Intermolecular means between the two, right? The hydrogen bond formed in between the two molecules, what we call intermolecular hydrogen bonding. Those liquids, containing intermolecular hydrogen bond is difficult to escape as the vaporized. That means, so that liquid having the low vapor pressure, those molecules, those liquids, containing only the intramolecular hydrogen bonding, so that the liquid can easily vaporize. See, for example, in our chemistry, one of the compound that we show you, this is the benzene ring, as we know. So if I write a OH, that is what we call the compound phenol, right? So one of the hydrogen is substituted by the one of the key. Just I write here one of the compound. This is the what we call the key. This is the NO2. I write in the form of the bonding structure. So this is the what we call the nitro. This is the OH group. Here, this position here. This is the carbon. This is the carbon. So what a position? 1,2 position. So at the 1,2 position, this OH group and this NO2 position is what we call ortho position, right? So at the ortho position, this hydrogen can be bonded with this oxygen, right? So that type of the bonding, what we call intramolecular. So another types of the this compound. When we write OH here, I write NO2 is here, right? I write O is here, double bond, oxygen is here. This is the partially negative charge, and this also partially carry the positive charge, right? So this negative charge and positive charge, so since these two are very far distance, here these two is very close. So this minus charge, this plus charge can be attracted very easily. But here since these two are very far away, so another molecule when we come closer, see nitrogen here, oxygen, another is oxygen here, then here can be right like this. So this oxygen can be closer to this hydrogen and can form the bond. See, this is the one of the molecule. Here, what is the position here? If I count it from here, 1, 2, 3, 4 here, if I count this side, 1, 2, 3, 4. So this is the 1, 4 position. What the name of this isomer we call the para position. So the name of the compound here, the name of the compound here, but same compound, but the position different. Since the position different, this compound what we call ortho nitrophenol. This is the para nitrophenol. See here, this nitrophenol, ortho nitrophenol. So since this intramolecular hydrogen bonding is formed, this liquid, as I said, this is the liquid. Yes, no, this liquid is more volatile. So this one is not a volatile because very big molecules, very big molecules forms. So since these molecules cannot escape as a vapor, so these types of the liquids cannot be vaporized easily. So that means non-volatile, right? Now here, so that I mean liquids, we have the some case very weak bond between the molecule. That bond we call intermolecular hydrogen. Those liquids having the intermolecular hydrogen bond difficult to escape as a vapor. That means that liquid having the low vapor pressure. Those liquids containing the intramolecular hydrogen bonding or no bonds formed, that types of the liquid are very high vapor pressure. That's the different nature of the liquids. Number 2. Even our so water, so we form that the types of the intermolecular hydrogen bond. So number 2 factor is the effect of temperature. Temperature, you know the temperature. What's the role of the temperature? Temperature always doing what? Breaking the bond. At high temperature can break the bond. At low temperatures, the bond is very stronger than at high temperature. So when temperature increase, bonds start breaking. So this hydrogen bond is normally weaker bond. So when we supply the temperature, means when we supply the energy, when we supply the heat, so bonds start breaking. So once the bonds completely break, so that molecule is free to escape as a vapor. Understand? Therefore, when the temperature increase, the vapor pressure of the liquid also increase. That means vapor pressure of a liquid increases with increase the temperature. Don't forget, right? Then one of the most important factors is, see, in our liquid, this is the pure liquid. You know, pure liquid. Okay, this pure liquid has own vapor pressure, right? On vapor pressure. What's the vapor pressure? That is another case. So that pure liquid having the own vapor pressure. Say for example, water. Pure water. What is the pure water? What's the vapor pressure of the pure water? That is 760 millimeter of mercury. That means 760 atmosphere, right? So this is the vapor pressure of the pure water, right? Now, when we add the another liquid, right? So that is another liquid, not water. When we add another liquid, so different liquid have a different vapor pressure. Understand? So this may be liquid, this may be solid, right? Okay. So some little amount of the liquid when we add into our given liquid, so this vapor pressure of the pure liquid should not be remain there. So it should be changed. it should be changed, right? So how this vapor pressure of the pure liquid what we already having, so how it's increase or decrease, that's the question, right? See, the common sense is when we add some amount of the liquid, so it should be non-volatile liquid, non-volatile substance, we can say the little amount, so we can say that is a solute. When we add a little amount of the liquid or non-volatile solute into our liquid, what will be the effect of this vapor pressure, right? See, before I telling you, when we mix together, when we mix these two, so ultimately that is what we call a solution. See, when we mix it, it's now becoming a solution, right? So I just tell you what is the vapor pressure of this solution. We used to asking you. See, before we added our any substance that is the pure liquid, after we add in something that's now become the solution, now we have a two question here but same answer. What is the question is how is the vapor pressure of the liquid when we add some amount of the non-volatile solute added? That's the one question. Another is, okay, what is the effect of vapor pressure of the solution, okay, when we add some amount of the solute add into the pure liquid? So that is the different question which can ask you. But only the thing is that when we add some amount, okay, some amount of the liquid, maybe in terms of the volume or in terms of the gram, in terms of the mass, when we add some amount of the non-volatile solute into the liquid, the vapor pressure of that pure liquid, it should be decreases. That means reduce or lowering. Say for example, the vapor pressure of the pure water is 760. When we add some solute or some liquid or some solid non-volatile, when we add it, the vapor pressure of the pure water 760 will not be 760, will be less than 760, maybe 750, maybe 758, 59, so and so. That means 700, less than 760, less than, right? So that is our important factors affecting on the vapor pressure of the liquid in our liquid, right? So one of the important factor is how much amount of the solute we add into the given liquid, right? So the lowering of vapor pressure of our solution, it depends on the amount of the liquid we add here. If you add more amount of the solute added, the lowering of the vapor pressure also be more lowering, more. That means more lowering, more amount. Less lowering, less amount. So that's the very important to understand about our vapor pressure of the liquid. So on the next class, let me discuss what's the importance of the solubility of a liquid in a liquid. So we have a very important law what we obey in this solubility of a liquid in a liquid. That is the name of the law. Let me write here, Raoult's law, right? So on the next class we'll discuss about it, Raoult's law. So till then, let's be just try to understand this much for today. Okay then, see you, right?